In this lecture we are going to talk about the introduction to differential equations. So this is introduction to differential equations. Introduction to differential equations. Differential equations. Sometimes we just call it DE when you want to say differential equations. Sometimes we just write DE, okay, for differential equations. So what's the differential equations? So this is first I would like to say that this is the applications of calculus actually. So this is the applications of calculus. Applications of calculus. So you learn calculus 1 and 2, or maybe you have already taken calculus 3. So what we're trying to do in this class is we're going to talk about applications of that. So you're going to see that many of the things that you learn in your calculus classes are repeated here. Okay. So let's start with the basics. So the first important one is the independent and dependent variable. So let's talk about independent and dependent variable. So what's the independent variable? So independent variable is a variable that can take any value in a domain of a function. So independent variable. So we can say that a variable sometimes we just write like x, t, u, things like that. So these are what we normally use for independent variable. There's no rule, but these are the common things that we use. Okay, the distance, time, those kind of ones. A variable that can take any value. A variable that can take any value that can take any value. We can say any value in the domain of a function. Why we write that part, it will be clear later. Any value in the domain of a function. This domain is important because you can't simply pick all the values. There's a domain that we talk about, okay, but I'm going to give you an example in a minute. So and then we have the dependent variable. So this is the dependent variable. So what's the dependent variable? So it name tells everything. It says depend. Yes, it depends on the independent variable and what we normally call the model equation, because we have an equation that you need to find the dependent variable. So it's also depend on that. Okay, so we can say that a variable that depend on the independent variable, or a variable that depend on a variable that depend on a variable that we can say depends on the model equation and the independent variable. Okay. Yeah, a variable that depend on the model equation and the independent variable. What we mean by these? So for example, let's look at a situation. So I'm going to give you this one. So let's say two examples. So let's say we have y equal 1 plus x to the cube. So you can see that in this case, so the x is the independent variable. You can see x can take any value. so we can say x belongs to the interval negative infinity to infinity. So x can take any value. What about y? And you can see there's a cubic function. It's go from negative infinity to positive infinity. So that means in this case y also take any value from negative infinity to positive infinity. So that means here the independent variable can take values from negative infinity to positive infinity. Dependent variable also can take values from negative infinity to positive infinity. What about this example? Let's say we have y equal, I'm going to say 1 over x minus 2. 1 over x minus 2. This is my x, okay? 1 over x minus 2. So you can see that in this case, x cannot take all the values. There are, so that's why you have to be careful when we say that's why it's the domain of the function. So in this case, you can see that x cannot be equal to 2, because if x equals 2, then you divide by 0. So that you need to avoid. So that means now in this case, you can say x belongs to not all. It's going to go for negative infinity and stop at 2, open, and union can start at 2 and go to infinity. So that's what happened in this case. So you have to remove 2 from the domain. And then what is y? And you can see that if you think of the graph of this function, this can never equal to 0. You can see that there's no value that's going to give you y 0. So that means you're going to get everything except 0. So you can say all real numbers, this is a set of real numbers, all real numbers except 0. So you can remove 0 from the values. So this is how it is. So all real numbers except 0. You never get 0, because if you look at the graph, actually I can draw the graph here. You can see if you look at the graph of that function, so what's going to happen at 2, so there's asymptote. Remember from algebra, there's an asymptote here. And then what's going to happen, this part going to go like that, and this part going to go like this. So that is the shape of the graph. Okay, so so if you go from negative infinity to positive infinity, this is what it looks like for the second function, and you can see that it never equal to 0, but and also you can see that x the independent variable can never pick the value 2. Okay, so that's the graph for the second function. Okay, so now let's try to talk about what is a differential equation. So before we talk about, let's talk about what is a derivative. Okay, so what's a derivative? So what is a derivative? What is a derivative? Remember, this is what you learn in your Calc 1 class, derivative. So now we can use them. Okay, so what is a derivative? So derivative, I mean, you can simply say that is the rate of change of the function. Okay, so we can say the rate of change. The rate of change. That's a derivative. Rate of change. Rate of change is called. This is like simple version of that. Okay, it's easy to remember. The rate of change is called. Rate of change is called the derivative. It's called the derivative. Rate of change. So you have you want to think about rate. So that means it's depend on something. So like so in a more specific form, you can say that. So this is like kind of better way to say it. So you can say that the rate of change of y, the rate of change of y with respect to, so we normally write w RT with respect to x. So you can see that what are these x and y? So that is the independent variable, and that is the dependent variable. You can see that with respect to x, because x is the independent one. So you can change the independent one, and then you will get the dependent one. So it's an independent variable, and this is a dependent variable. Okay, those two are important. And then we know that just to not this, like we have a notation for that. So the notation is, we're going to normally write this one as dy by dx. So that means the order matters. So you can see what we normally write is we can write the independent variable in the bottom. That's the independent variable, and then we write the dependent variable on top. Okay, that we normally that's how we write this one. When you write the notation, the bottom one is the independent variable, the top one is the dependent variable. Okay, good. So let's look at some of the examples. So how about few examples? So let's say examples. So let's start with something that we know. For example, when you drive a car, you're going to see the odometer reading. Another odometer is speedometer. Okay, so you can see speedometer. So where you're going to see the speed reading, speedometer reading is the rate of change, the distance traveled by the car. The speedometer reading is the rate of change speedometer reading is the rate of change of the distance traveled. You can say traveled by the vehicle. Okay, so that's the speedometer reading. Speedometer reading is the rate of change of the distance traveled by the car. So you're gonna see the derivative right in front of you most of the time. And let's look at another one. So what about the slope? So the slope of the tangent line, the slope of the tangent line, the slope of the tangent line, the slope of the tangent line. Okay, the slope of the tangent line, you can say is the the slope of the tangent line is the, you can say, derivative or rate of change. Okay, is the derivative of the two quantities plotted. What does that mean? So it simply means that, so if you have a graph, here we have the independent variable and the dependent variable. We normally put the independent variable on the x-axis. That's the kind of common thing to do. Then you're going to actually see it as the slope of the tangent line. If you change the order, the slope doesn't give you that. Okay, so you have to make sure that the independent variable always goes to this side. You do that, when you do like physics or chemistry. You put the independent variable there, so that's the reason. Then the slope exactly becomes the rate of change. So like that. So that's the derivative. Okay, so we normally write this one as y prime. Remember? Okay, good. And then more examples. How about more examples? So we can say that the velocity, as we discussed in terms of velocity is the derivative of the displacement function, is the derivative of the displacement function. Just one more example. So this is very clear. The velocity is the derivative of the displacement function. It's a displacement, it's a vector now. Okay, speed is the derivative of the distance function, because that's a scalar. That's two difference. And then as the last example, we can see when we apply a force, we change the rate of change of the velocity. We change the rate of change of the velocity. Okay, so when we apply a force, what we're going to do, we change the rate of change of the velocity, that we normally write the dv by dt. We normally write this one like dv by dt. If you say v is the velocity, so we're going to change the rate of change of the velocity, dv by dt. We normally call this a, the acceleration. Okay, this rate of change we normally call the acceleration. Okay, so we change the acceleration. So these are the kind of examples that we see as the derivative. So what are the notations that we're going to use for derivatives? So we can use some of these notations. So we can say notation. Okay, so there are several notations. For example, the most common one we write as dy by dx. In some cases, if the x is the dependent variable, we might write dx over dt. In this case, t is the independent variable, y is the dependent variable. And also we can use the prime notation. So y prime, if you have higher derivatives, y double prime, like that. Also we can write this is the third derivative, so d3y over, you can say dx3. This is what we normally call the Leibniz notation. This is the Leibniz notation. Notation. So this is one of the mathematicians who developed the theory about 2 centuries ago. It's called Leibniz. Okay, now let's talk about the differential equation. So what's the differential equation? So now we know what is the derivative. Okay, let's talk about the differential equation. What is a differential equation? What is a differential equation? Let's make it short. So what's the differential equation? An equation, okay, an equation that contains a derivative. That's it. Okay? An equation, it has to be equation that contains a derivative is called a differential equation. It's called a differential equation. It's called a differential equation. It's called a differential equation. Let's look at some examples. So here are some examples for that. So examples are, you can say dy over dx plus y equal x, and you can see that it has a derivative and it is an equation, so it is a differential equation. Okay, so you should see the equal sign and you should see a derivative, some kind of derivative. Okay, so that's a differential equation. And how about this one? Y double prime, the second derivative, plus 3y prime plus the independent variable equal 0. So you can see it's an equation, it has some derivative, so it is a differential equation. And what about this one? D squared y over dx squared plus 4x equal sin x. So you have to think about what is the independent variable. Here the independent variable is x. Okay, in the previous one independent variable is t. The first one independent variable x again. Okay, so the last one is also a differential equation because there's a derivative and an equal sign, and there's a second derivative there, so there's some kind of derivative. Okay, so what we talk about, so we have there's a derivative and there's an equation, equal sign, so we have more derivatives here, and there's equal sign, and there's a derivative here and there's equal sign. So these are all differential equations, and in this class we're gonna learn how to solve all these three types. We might need to wait several weeks until we're gonna solve some of them, but we're gonna solve all of them in this class. These are different type of differential equation. We need different techniques to solve them. Okay, so we're gonna talk about all type of I mean not many, but I mean we're gonna talk about quite a lot. Okay, so simply you can say that this is kind of a nice way to say it. Anything that changes, anything can say anything that changes, anything that changes can be written as a differential equation, can be written as a differential equation, can be written as a differential equation. So it's kind of interesting. Anything that changes, can be written as a differential equation. And then the highest derivative appeared is called the order of the differential equation. So you can say the highest derivative appeared is called the highest derivative appears is called the order of the differential equation. Okay, it's the order. We call that the order. So that means the first one is a first order differential equation, the second one is a second order differential equation, third one is also a second order differential equation, because that's the highest derivative appeared in the equation. Okay, highest derivative appeared in the equation. Okay, good. And I can also give you a little complicated ones, but we can talk about later. There are some other complicated situations. Okay, so let's look at this one. So let's do this. So another example, let's say dx over dt plus x equal 2 cosine t. Okay, this is one of the equation appears in the textbook. So you can say, so this is a first order. Why? So this is a differential equation of it's very clear, and highest derivative appeared is a first derivative. So this is what we call, so is a first order differential equation, first order differential equation. Okay, of the you can say of the dependent variable x, and the independent variable t. Okay, dependent variable x and the independent variable t, because that's in the bottom. Okay, so those are the basics of differential equations. So let's talk about some solution. What we mean by a solution. So solution of a differential equation. Solution of a differential equation. The solution of a differential equation. Okay, the solution of a differential equation. So so what we mean by solving a differential equation? What do you mean by solving a differential equation? Solving a differential equation means you try to find a function, dependent function y or x that satisfies the differential equation, right? So so we can say but before that, when you want to solve a differential equation, it can be quite hard most of the time. So it's not like an obvious situation. So that is one of the reasons why we need the integrals. So the solution method involves the integration, the reverse process or the inverse process of derivative, because you want to go back. So that means that's why we need to kind of know about the integrals first, because it's basically about integrals. Okay, so so you can say solving a differential equation. Okay, so solving a differential equation can be you can say can be either hard or even impossible. So there are some differential equations you can never solve. So there are situations like that also. So solving a differential can be either hard or impossible. So and then so there's a small class of differential equation that you can solve. That's what we're going to talk about. Okay, it's a very small class. There are a lot of differential equations that you cannot solve. So there is a small class of differential equations, small class, okay, of differential equations that can be solved. Solved. It's kind of interesting. That's a small class. Okay, not very many. So we can say. So then, what do you do if you cannot solve directly? Solve means you try to find the exact solution, implicit solution, actually explicit solution for this one. But sometimes what you can do, you cannot exactly find an explicit solution. In this case, what we do, we're going to find what we call the numerical solution or the approximations. Okay, so in this case, if you cannot solve, then we find we may find approximations. Okay, so we can say we may find approximate solutions. Of the differential equation when you cannot solve, and this is what we normally call the numerical method, so numerical analysis. Okay, see what we normally call numerical method. Okay, we can talk about two very important techniques in this class, the Euler's method and the Runge-Kutta method. So that's later. Okay, so we can talk about those two. We can talk about two such situations, how we can do, because it's going to help you. So we can do what we call the Euler's method, and then also we can do Runge-Kutta. So Runge-Kutta, okay, method. So we can talk about those two techniques later. Okay, good. So let's try to talk about what we really mean by solving an equation. So let's talk about the algebraic case first. The easy one. So let's talk about solving an equation. Okay, so solution of an equation. Okay, the algebraic equation in this case. So let's say we have. So what we do in this case? So if you want to solve an equation, what you do? Find x. So we can say find x means the variable. Okay, find x that satisfies. Find x that satisfies the equation. So that's what we mean by solving equation. Find x that satisfies the equation. For example, if we have x squared minus x minus 6 equals 0, and we know that if you want to find x, so that there's a systematic way to do it. What the systematic way? We're going to factor it. So what are the factors? X minus 3 and x plus 2 equals 0. And then what we can do, that's the product. So we're going to set each one equal to 0. So x minus 3 equal to 0, or we're going to say x plus 2 equal to 0, because we know that at least one is enough. That's why we say O here. Okay? We don't need both. So the first one going to give you, if you add 3, you're going to get x equal 3, or you can say x equals -2. So those are the two solutions. So we have two solutions for this one, x equal either -2 or put a comma and 3. So those are the two solutions. Why we say these are solutions? Once you plug in that, you can see it's going to work. So that's how you know it's a solution. So now, so this is the way to find it. And then there's another one what we call the verify. Verify means you're not going to really find it. So someone says that, okay, this is a solution. Okay, so we verify whether that's a solution. What do you do? You plug in that into the equation. So we plug in. Okay, so we're gonna plug in. We're gonna plug in. Let's say x equals -2. Okay, so if you plug in that, so let's plug in wherever you see x. So that means it's gonna do -2 squared. That's the first one, minus -2 minus 6. So let's simplify. And -2 squared means 4, minus -2 means +2, minus 6. You can see that is simply you get the 0, so that means satisfies the equation. You get 0. You start with one side. You normally start with the complicated side and try to simplify and get the easy side. Okay, so we start with the difficult side. Start with the difficult side and try to get the easy side. So that's one way to normally do it. That's gonna make it fast. Okay, so we're gonna say equal, that means satisfies. So we equal is satisfies. Okay, so satisfies. So that means satisfy means therefore you can say x equal -2 is a solution. It's a solution of x squared minus x minus 6 equals 0. I mean, that's how we can completely write that last sentence. Okay, because it's going to complete the solution process. So we have to write the last sentence. Okay, so it's important. What I mean by last sentence is this one. So we will write something like that whenever we solve a equation like this. Okay, so let's talk about a situation that involves a differential equation, solving a differential equation. Okay, so the solution of a differential equation, what is that? So solution of differential equation is not just finding a variables, not of just finding values, but now we need to find functions. Okay, so what we're trying to do is find a function. Okay, so find a function. Okay, so I just write function like that. Okay, function, the shortcut. Okay, find a function x or whatever the dependent variable you have. Okay, find a function x. Find a function x of t. That's the independent variable. Okay, that's the independent variable. That's the dependent variable. You need to change the word, change the variable depending on what you have. That satisfies the differential equation. That satisfies the differential equation. So that's simply what we're trying to do. Find a function x of t that satisfies the differential equation. And you can see that this is not really obvious. Okay, so it's not obvious to us. Okay, it's not obvious. So that's why we try to learn several techniques in this class and how to do that. So you need to learn how to do that. So after we learn a few techniques, so after 2 weeks you're gonna learn a lot. Okay, you're gonna learn a lot, and you can solve a lot of differential equations. So so let's look at a situation like this. What we can do this one. So let's talk about this differential equation. So we have dx over dt plus x equal to cosine t. Okay, so in this case it's very clear. The t is the independent variable and the x is the dependent variable. Okay, so it's a dependent variable. It's always a good idea to figure out what is the independent variable and what is the dependent variable. That means you need to find a function of x. You need to find a function of t. Okay, find a function of t. So we normally write this as you need to find. So what you need to do is find a function of t. So we normally write this x equal xt. So that means it's a function of t. So we normally do that. Okay. So we just write just to make sure there's a function of t. So we say x, which is a function of t. Okay. So now the thing is that we don't know how to do that, but I'm going to say this question. So the first example would be, let's say, verify that. Okay. Verify that. So verify is completely different from solve. If I say solve, you have to wait like 3 weeks to do that. Okay. Actually more than 3 weeks to solve this equation. But when I say verify, that means I give you something, you check whether that is the solution. That's what verify means. It's completely different from solving. Solving is a real deal, but that we can do later. Here I'm going to give you something, some expression of t, and I ask you to check whether that's the case. Okay. So verify that x equal xt equal, let's say, cosine t plus sine t, cosine t plus sine t is a solution. So I say verify that. So I give you something. You see that? So I give you an expression. You want to check whether that's the case. So how you do that? What you do? You take the derivative and plug in. Okay. So that's kind of clear what we need to do. So let's do that. So let's take the derivatives and plug in. So taking derivatives. So that's the answer. Okay. So answer, taking derivatives, taking in this case just one, so I'm going to say the derivative, but sometimes you have to take multiple derivatives. So taking the derivative, so we have dx over dt. If you take the derivative of this function, what do you get? What's the derivative of cosine? It's a negative sign, so negative sine t, and then plus cosine t. So that's the derivative. Okay. So derivative of cosine, negative sign is cosine. That's what you get. Now what do? You're going to plug in that into the equation. So plug in into the equation. We have dx over dt plus x equal, so what is dx over dt? It is negative sine t plus cosine t, so that's the derivative part, plus x. What is x? X is cosine t plus sine t, that's the x. Okay. So you can see, so that is the derivative, this is the dx over dt, and that is the x. Okay. Good. Now let's simplify. Okay, so if you simplify, what you get? So you can see that some of the terms get cancelled. You can see this term get cancelled with that term, so you get twice the cosine. So you're going to get there's a cosine, so you're going to get 2 cosines. So 2 cosine t, and that's exactly equals the right side of equation 1. Okay. The right side of equation 1. So that means, you see, it satisfies the equation. You start with the difficult side and you simplify, you get the easy side. That means, therefore, you can say therefore x equal cosine t plus sine t is a solution of the differential equation 1. Okay. Therefore, it's a solution because it satisfies the differential equation. So let's do another one. So how about this one? Again, we can check that. X equal cosine t plus sine t plus e to the negative t is also a solution. Is also a solution. So what we do, you can see we add an extra term here, see, but you can see that that's still the case. Okay, so let's see whether that's the case. So we can check that x equal cosine t plus sine t plus e to the negative t is also a solution. So let's do the same thing as we did before. So what we're trying to do, so we're going to do state the derivative. Okay, so we have x equal cosine t plus sine t minus, plus e to the negative t. So once you take the derivative, so you're going to get dx over dt equal negative sine t plus cosine t minus e to the minus t, okay, by the chain rule. Okay, so if you use the chain rule, that's what you get. Okay, chain rule. So if you use the chain rule, you're gonna get this. Very good. So let's plug in that into the equation. So is that clear? So how to take the derivative of this function? If you have e to the negative t, what do you do? So you rewrite the function and then multiply by the derivative of the top function. Okay, derivative of the top function is -1. That's why this negative sign comes. Okay, so that's the derivative of the top function negative t. So if you take the derivative, you're going to get -1. Okay, that's the negative sign. Good. So if you forget that, this is the formula we use here. So if we try to find the derivative of e to a function, some function, it is simply e to the function, no change, and then multiply by the derivative of the function. Okay, yeah, so no change, so just repeat that. Okay, no change, and then multiply by the derivative of the function. That's what we use here. That's what we call the chain rule. Okay, for exponential function. Good. Now we're gonna plug in that. So once you plug in that, so we can say plugging in. So we're gonna get dx over dt plus x equal, so you can say dx over dt, we find that it is negative sine t plus cosine t minus e to the minus t plus x is cosine t plus sine t plus e to the minus t. And then what's going to happen, so we have, you can see some of the terms get cancelled. Actually, you can see that sine get cancelled, and also the exponential function. So I'm going to cut it a different way, then you can see what you did. Okay, so those exponential functions also get cancelled out, and you simply end up getting twice cosine t. That means it satisfies the differential equation. You get the right side. So that means that's also a solution. Okay, and then so you can see that. So can you give another example? Okay, can you give another example? For example, you can see x equal cosine t plus sine t. You know that part always work, and you can just pretty much multiply by any number. So for example, negative 0.7 e to the negative t. That also should work. Why? That 0.7 gonna repeat. Okay, that's gonna repeat. So that means still get cancelled. So right. So it also works. So that means in general we can write like that. So you can say in general. x equal cosine t plus sine t plus a constant times e to the negative t is a solution. So that's what we normally call the general solution, okay, for any c, okay, and then we call this is a general solution, okay, general solution. So we call this is the general solution, okay, we call this the general solution. So now what you can do is you can find special solutions. These are what we normally call particular solutions, special solutions. So for example, so we can say particular solution, particular or special, okay, special solutions. So we can find a solution that passes through a special value. So we can say, let's do an example for that. So, okay, so example would be find a solution such that we put s dot t dot such that, find a solution such that x0 equal -1. So you can find a solution that means that passes through the point 0, -1. Okay, so the point is 0, -1. It has to pass through that point. That's x value, and that's the x means x coordinate value. This is the y coordinate value. Okay, so but here remember we pick x as the dependent variable. Okay, so be careful with that. But in a general sense, we normally call x coordinate y coordinate. That's the x coordinate and y coordinate. So those are 2 points. So that means we try to find a solution that passes through that particular point. So what we do, what we know. So the answer is we know that x0 equal -1. So that means we're going to plug in that. So we're going to say, okay, x0. So that means plug in 0 to the function. So it is a cosine 0 plus sine 0 plus ce 0. Now we're going to say this is equal to 0. -1 is -1. So, but we know that the cosine 0 is 1. Cosine 0 is 1. Sine 0 is 0. E to the 0 is 1. So what do you get? You're going to get 1. So what this give you? This gives you 1 plus c equal -1. In other words, it says that c equal -2. So that means if you put c equal -2, that's a particular solution, that's a special solution that passes through the point 0, -1. Okay, that passes through the point c equal that passes through the point 0, -1. So let's look at several different cases that are going to give you different solutions. So yeah, so let's look at that. So good. Yeah, so these are some cases where it's gonna pass us through the different points. So for example, you can see that in this case, that's the point we are talking about. So that's the point 0, -1. So in this case, what happened is c is equals to -2. When c equals -2, that's gonna pass through this particular point 0, -1. So you can see that's the point 0, -1. So you can do the same thing. So if you want to find a value that passes through 0, 1, that's 0, 1, and then you can see you can do the same thing, and you can see that in this case c simply becomes 0. And also you can do a similar argument. So you can find a solution that passes through 0, 3, and if you solve, you can see that you're going to get c equal 2. Okay, so those are what we call particular solutions. Okay, particular solutions that passes through special points, and you really don't need that point at exactly at 0, so you can just pretty much find any point that you like. Okay, for example, if you want to find a curve that passes through that point that looks like 2 half, okay, so you can see that that's the point 2.5. May not be exactly same, but it's an approximation. So you can see that if you try to do that, you should get c equal 0 in that case. Okay, so something like that. So that's the idea. So you can see these are what we normally call particular solutions. Particular solutions. Okay, so let's continue. Let's do one more example just to see more about this. How about this example? Good. I thought it's clear. Okay, these are what we call particular solutions. So we have here 3 particular solutions of the differential equation. Okay, 3 particular solutions of the differential equation. So I want to warn you. So that means what you can see that if you have a differential equation, the solution is not unique. Okay, so solution is not unique. So that means if I say solve a differential equation, that means find all the solutions. That's what it means. Okay, so let's exaggerate that. So the warning. Okay, you can see solutions of a differential equation may not be unique. Okay, so that's very important. The solution of a differential equation may not be unique. So that means so solving a differential equation means solving a differential equation means find all the solutions. Okay, means to find all the solutions. All the solutions means the general solution. Okay, general solution normally contains constants. Okay, so depending on the degree, depending on the order. So if it's a first order, you're gonna get 1 constant. If it's second order, you're gonna get 2 constants, like that. But we can talk about that later. Okay, so yeah, so the solving a differential equation means to find all the solutions. Good. So let's do so the solving differential equation, we don't do that yet, so because we need more theories and more techniques. So we first try to do the verification. Let's do one more verify problem just to know a little bit more about that. So another example. So verify that x equal c1 e to the t plus c2 e to the negative t is a solution of x double prime plus x prime minus 2x equals 0. Okay, so here you can see you don't see the independent variable, you only see the dependent variable. So independent variable you can see is t, because you can see if you look at the solution part, the function part, you can see there's a t there. So you can expect that should be the independent variable. Okay, so again so the note is verify does not equal to solve. Okay, so solve means you have to use a technique to find x, but here x is something is given, some expression is given. So what you can only do is verify. You're going to verify it. Okay, so something is given, you're going to verify that that's a solution. So it's a different thing. Okay, so let's do that. So now you know what to do. You just take derivatives. Okay, so the answer, taking derivatives. Okay, taking repeated derivatives. Taking repeated derivatives Why repeated? You see that you need to take several derivatives here. So you're gonna x equal c1 e to the t plus c2 e to the negative t, and then we have x prime, which is, let's take the derivative. If you take the derivative, what do you get? C1 e to the t. By the chain rule, C2 is a constant, and e to the negative 2 e to the negative 2t. So when you take the derivative of the exponential function, you simply multiply the derivative of the top function. So that means it's going to be negative 2. So it's going to be negative 2 c2 e to the negative 2t. So it's very clear. By the chain rule, you simply multiply by the derivative of this function. Derivative of this function is negative 2. That's why you multiply by negative 2. So let's take one more derivative. So you're gonna get I'm gonna write it here. So x double prime, which is equals to c1 et, and if you take one more, you're gonna get, you multiply by negative 2 again, that become 4 c2 e to the negative 2t. Okay, so that's the derivative. And then now you're going to plug in. Okay, plugging into the differential equation. We have, so let's plug in. So we have x double prime plus x prime minus 2x equal, so I'm going to plug in. What is x double prime? Which is c1 e to the t plus 4 e c2 e to the negative 2t, and then plus x prime. What is x prime? c1 et minus 2 c2 e negative 2t, and then negative 2 times the function, which is c1 et plus c2e negative 2t. So you can see that these are the three things we plug in. So this is the x double prime, this is the x prime, and that is x. Okay, so we're gonna plug in that all three, and then we're gonna simplify. Once you simplify, what's gonna happen? You can see that a lot of things get cancelled. So I'm gonna cancel them. So you can see so we have c1 et and negative 2 c1 et. That means these three get cancelled, and then also we can see that we have 4 c2e negative 2t, negative 2 c2e negative 2t, and then negative 2 c2e negative 2t. So all three get cancelled as well. So this cancels with these three because you have negative 2. So that means you simply get 0. So that means a solution. Okay, you can see 0. So you can see that 0. That means it is a solution. Okay, it is a solution. So therefore x equal c1 et plus c2e negative 2t is a solution of the differential equation x double prime plus x prime minus 2x equals 0. Okay, so now what we're going to do, so it's very clear. So what we did, we take the derivatives and plug in, and then we see that we get 0. If we do not get 0, it is not a solution, but we get 0. Now let's try to do so we can say, I'm going to extend the problem now. So how we can extend this? So we can say something like this. We can say find, so this is the second part of the problem, find c1 and c2 such that x0 equals 0 and x prime 0 equal 12. Okay, find c1 and c2 such that x0 equals 0 and x prime 0 equals 12. So how to do that? What we're gonna do, we're gonna plug in, okay, the conditions. So we can say since x0 equals 0, we're gonna plug in. So what we get? So we're gonna get we can say x0. X0 means wherever you see the independent variable, plug in 0. So you're gonna see the independent variable at, so it is c1 e to the 0 plus c2 e to the negative 2 times 0, but which is equal to 0. That's given. That's 0, and this is this 0. Okay, this is two different zeros. And then what's gonna happen? You can see that in this case this is 1. This is also 1. So that means this gonna give you c1 plus c2 equals 0. I'm gonna call this equation 1. Okay. And then do the same thing. We also have x prime 0 equal 12. So if you do that, then you can see that x prime 0. So go to the prime, so derivative, and plug in 0. So if you go to the derivative and plug in 0, you're gonna get c1 e to the 0 minus 2 c2 e to the 0 equal 12. And from this you're gonna get c1 minus 2c2 equal 12. I'm gonna call equation number 2. Now the question, how are you gonna solve them? So this is a simple college algebra task. So what's the best way to solve this one? I'm not going to use the elimination method here. I will use a I'm not going to use a substitution method here, because substitution method can be really lengthy. So I'm going to use the elimination method. You can see that you can remove one of the variable by doing some simple algebra. For example, if you multiply the first equation by 2 and add it to the second one, you multiply the first equation by 2 and add it to the second one, you can see c2 get cancelled. So that's the fastest way to solve this. So you can say by, okay, that's how you're going to solve this one, by 2 times 1 plus 2. Okay, by 2 times 1 plus 2, we're going to get 2c1 plus c1. Is that clear? Because if you multiply the first equation by 2 and add it to the second equation, c2 get cancelled. So you only get 2 times c1 plus c1 from the second equation, which is equals to 12. Okay, and this can give you 3c1 equal 12. In other words, c1 equal 4. So if c1 equal 4, if you go to the first equation or any equation, and you can see that c2 equal negative. Okay, just use any equation. Good. So that means you're gonna get the other two values. So this is what we call the particular solution. Okay, and you can see that these values are given at 0. You can see that these values are given at 0. So therefore we call these are initial value. Okay, so therefore the solution to the initial value problem, therefore the solution to the initial value problem, why we call initial value? Because the values are given at 0, so you call initial value. So therefore the solution to the initial value problem is, you can say xt equal, we can plug in that 4e to the t minus 4e to the negative 2t. So you can see it's not that difficult, but there are simple things that we need to remember. Okay, so I'm going to give you an exercise problem for you to try, so you can try this problem. So we're going to say, so let's do this. Good. So it's for you to try. Okay, so that's an exercise. So we can say verify that. Okay, verify that y equal a e negative 2x cosine x, so it's a product, okay, plus b e negative 2x sine x is a solution of y double prime plus 4y prime plus 5y equals 0, and then find a and b such that y0 equals 0 and y prime 0 equal 3. Okay, so you can do this as an exercise, and if you get stuck, let me know, so we can discuss how to do this kind of problems. But you can see it's pretty much the same thing, but now you need to use the product rule. So you use the product rule because you see product, so use the product rule and plug in there, and you can see that it works. Okay, we say verify, and then after we do that, then what you can do, you can use the two initial conditions to find a and b as we did in the previous problem. Okay, and then later in a different chapter we can talk about how to actually find the solution. So where this is coming from, where this why you have like exponential and cosine function here and the exponential and sine function here. So there should be a reason for that, but this we can discuss later. Okay, so we need to wait like about 3 more weeks for that. Okay, so this is the end of the first part. Thank you.